Hello, everyone. This is Professor Ma, and this is the summary monotone sequence. By monotone means it goes in one direction. So we have the following more precise definition. We say the sequence keeps going up. Okay, think of this sequence now on y-axis, and here's an plus 1 has to be higher than that, an plus 2, and so it keeps going up. Then it's increasing. And it's non-decreasing if it's bigger than or equal to. You may stationary for a while, then start climbing, or stay there for whatever. Decreasing, going down. Pictures, an is here, is y-axis, and then this, and then an plus 1, this downward, on this, so getting smaller and smaller, so decreasing. And non-increasing is if we replace it by equals and equal sign, but greater than or equal to. Here are examples of each type. I'll let you read it. And all these sequences, we say they are monotone. Basically, they're going in one direction. They don't turn around, go backward. And specifically, these ones where the inequality are strict, we call these strictly monotones. So increasing and decreasing functions are strictly monotone. How do we test for monotones? Well, let's do the example for increasing sequence. We can do an algebraic test. What type of algebraic test? Well, if we know the formula, can take the difference. An minus an plus 1, the latter terms must be bigger than the previous term, so the difference must be positive. So if that is true for every number n, then this sequence is increasing sequence. And all can take ratios, divide. And which one do we use? It depends on how the algebra works. If we use the ratio test, probably better. If when we divide, a lot of terms will cancel out. I mean, a lot of factors will cancel out. Excuse me, not a lot of terms. And for difference, want to clean up the terms. And for the ratio, we want to make sure when we divide, a lot of factors gets canceled out. And then there's a derivative test. If I know the formula that defines the sequence, and let's call that formula A of x, and an is evaluating n for x. And I take the derivative of these functions, a prime of x. And if it's positive, means the slope is positive, means the function curve is climbing, going up. And the sequence, of course, has to follow that. As n gets bigger, it gets dragged upward and keeps going bigger and bigger. Okay. And then all of these inequality sign I can replace by backward. Then I can replace the word by decreasing. Okay. And similarly, let you read for the non-decreasing, non-increasing cases. We replace them with equal sign. Okay, so the main things about the monotone sequence is that since I know all the numbers are going one way, then there are two behaviors. Either they go up and it's stationary and has a limit, or they go up and keep going up higher and higher, do not come to a limit. So it either converges or it goes to infinity. In particular, if I know all the numbers are going up, points are climbing up, and it gets higher and higher, an, and then next one, an plus 1, they become bigger and bigger. But same time, we know one more information. Every one of them is below A. Well, then these tell us then this sequence of increasing sequence, there must be a point that's the limit. They must accumulate, they must bump into each other's, okay? If they keep increasing, then they have to bump into some kind of invisible wall, and that's the limit. So that's the fact about monotone sequence. Okay, this is true for monotone sequences. Here we have some tests, some example of sequence justifying that is, this particular one asks us to justify this is a decreasing sequence. So from here on, we will do start making proofs. We want to justify its decreasing sequence. You cannot mathematically cannot just write out a few terms. Say, oh, when n is 1 is 2 over 2, when n is 2 is 4 over 6, when n is 3 is a over 3. No, this is 2. 2. When it's 1, this is 1, sorry. 1, 2, and 3, this is 6. And when n is 4, this is 2 to the 4, 16. Then 6 times 4, 1, 2, 3, 4, 24, etc. I say, oh, well, look, it's decreasing. This is bigger than that, bigger than that, bigger than that. This is bigger than equal to. Okay. But how do we justify it? And so this is the proof. We need a proof for it, and the proof we're going to use the ratio methods. Okay, and here's a typical proof that we're going to use do later on. So we tell the readers what way we're going to prove it, how we're going to demonstrate it. We're going to use the ratio methods. What ratio method here? We're going to show the inequality. Since it's decreasing, we want to show this is less than 1. As it gets further and further, the terms get smaller and smaller. So divide. And here's a trick, and an plus 1 divided by an. And a lot of these calculations, we're going to treat the an underneath as 1 over an. In other words, flip an. Okay, flip an. So you take an plus 1 times flip an, and this is what that is. So this is an plus 1, and this is an flipped. So you just make a product. You skip one step. Sometimes this formula alone, you don't want to write many steps. So you just turn an over. And then continue with the algebra, cancel. And the most important things about the factorial is they cancel. For instance, a plus an, if I write out these terms, n times n minus 1, so on down to 1, is n plus 1. The tail end of the longer one is the shorter one. So I can cancel that. So I got 1 over n plus 1. Okay. And if this is n plus 2, then I will have another term over here, n plus 2, n plus 1. And then I will have gotten 1 divided by n plus 2 times n plus 1. So this is the reason we usually use quotients to handle compare formulas with n factorials in them, because by dividing, they will cancel out. You'll see this trick over and over again from here on, all the way to power series, stuff like that. When we talk about power series. Okay. And this number, of course, is smaller than 1. Because for m go to 2, 3, 4, and then the denominator gets bigger, so it's less than 1. Hence, this is a decreasing sequence. So this is a typical mathematical proof. Okay, again, you declare what you're going to do, and you demonstrate it, clean up the algebra, saying, oh, this formula obviously is less than 1. Therefore, fits the description of the theorem that Therefore, this sequence is decreasing. Eventually monotone. The front part of a sequence doesn't matter what it does, can oscillate, go up and down, but if beyond certain point it become monotone, you keep going up, then the front part is really doesn't matter if we want to study the whole behavior of the sequence. So if a sequence, I can throw away finitely many front portions and the sequence becomes increasing, decreasing, become monotone. We say this sequence is eventually monotone. Okay, meaning it goes up and down for a while, then it starts doing something that's steady, going monotone. Okay, and so all the, for instance, this is eventually increasing. Okay, so we say for sufficiently large n, this sequence is increasing. And in this case, we're talking about beyond the third n3, beyond the third point, third terms, then the sequence is monotone increasing. And we say a sequence is bounded above if there's a number like we just draw before, that's on top of it. Here's a number A, and the sequence is bounded above. If everybody in the sequence is down here, A, somewhere in here. Okay, so there's a ceiling. So bounded above A is we can view A as a ceiling. Okay, and if it's bounded below, there's a roof. There's a floor. Okay, so it means there's a B bounded below. So every term in A is in here, then this is bounded below. Yeah, I use letter A again. That doesn't matter. Okay, and if it's bounded above and below. So now I have to use A and B. Okay, so both above and below. Okay, so here is a bounded sequence. Sign is always between 1 and -1, but sign of n, I don't know, it has this sporadic chaotic behavior. It's bounded between 1 and -1, but I don't know the behavior. I cannot tell the patterns. The important theorems about monotone sequence is a bounded monotone sequence has a limit. It converges. A monotone sequence that's trapped. Okay, so the number keep going downward, but but has a floor underneath. It has to have a limit. Okay, again, it has a cramp downward. Each one is going to start bumping into each other. Not really, but they're going to be squeezed. And similarly, if the numbers keep going up, but there's a ceiling and they keeps going up, so they have to get closer and closer to each other. They have to get to a limit. It has to be a wall there that they couldn't cross, and that's the limit, which means it converges. So eventually monotone sequence, if it's bounded, it converges. If it's not bounded, then it diverges. Not only diverged, it goes to infinity. Okay? Because one way or the other. Because there's no ceiling. If a number going up, you cannot put a ceiling on top of it. Every time you put something on top of it, somebody is going to go outside and it keeps climbing, then it bounds to go to positive infinity. Okay? So this is the important fact about the monotone sequence and being bounded or not. Because from here, we can conclude whether monotone sequence converge or goes to infinity diverge. No chaotic behavior for monotone sequences. Cool. So these are picture image, okay. Okay, so can read through the statements. And finally, here is another example of how to show something is decreasing and converges, okay? And what we're going to do, we're going to show this sequence is bounded above and below. This sequence is positive, so obviously it's bounded below. So these numbers is going to be trapped above 0. Okay, so all these numbers going to be up here. We're going to show it's actually decreasing, and hence it's converges. Okay, so therefore we're going to show it's decreasing. Okay, and the easy way to show this is that converges. It just do the algebra to divide by 2n, 3n. The limit problem. Treat as a limit problem. Show the limit go to 0. Okay, but what I'm going to do is that from a different approach, kind of longer way to do it, through the idea of decreasing, and it's bounded. Therefore, it must have a limit, which is 0 if we calculate it. But we'll show that the difference is less than 0. As it goes further, it gets smaller, so the difference is negative. And so the algebra goes through the algebra, then finally we wind up with this collect like term to get this algebra. And the number n is bigger than 1, 2, 3, 4. So for whatever n is, this term is negative, this factor is negative. And therefore, the product is negative. Therefore, the difference is negative, always negative. Therefore, this sequence decreasing. So, but on the other hand, it's bounded below by 0. So therefore, it has a limit. Later on, we'll have sequence which we cannot quite tell what the limit is, but we know it's bounded in increasing or decreasing. So we know there's a limit. Finding the limit and showing it exists are two different things. And for later section, we'll clarify that more and more. So this is about monotone sequences. Okay, bye-bye. Adios.